Assalamualaikum and a very good day. We are from Group 9. Would like to present our final project titled Deflection of Beam. First of all, I would like to introduce myself and my group members. My name is Munkis bin Makno. Next, Muhammad Syahrul Izzuddin bin Cik Ros, Zul Iman bin Hamzah, Muhammad Alim bin Zakaria, and lastly, Muhammad Irfan bin Saiful. For introduction, deflection in structural engineering terms refers to the movement of a beam from its original position due to the forces and loads being applied to the member. It is also known as displacement and can occur from externally applied loads or from the weight of the structure itself and the force of gravity in which this applies. Deflection can occur in beams, trusses, frames, and basically in other structure. Next, our objective for our case study are: first, to evaluate the maximum deflection of the beam; second, to calculate the elastic strain energy with different materials; and lastly, to identify which material suits for the diving board.
Assalamualaikum warahmatullahi wabarakatuh. My name is Mahmod bin Ros. Now I will talk about the case study from our project, which is to find the maximum deflection and strain energy of diving board. So in our project, we're studying and analyzing about the difference of deflection and elastic strain energy of the diving board with a different material. So generally, we know the diving board is designed as a cantilever beam. Like this. So this is an example of the cantilever beam, which is one side of the board is fixed and the other side is beyond the support. So this side, so one side is supported and the other side doesn't have any support. So in this project, our objective is to calculate the maximum deflection of the diving board and determine the elastic strain energy of the diving board, and then the last one to compare with different materials, which aluminium diving board and wooden diving board. So aluminium diving board we have here, and the elastic modulus for aluminium diving board is 69 gigapascal, and for wooden diving board the elastic modulus is 3 gigapascal. So for the deflection, theoretically, when deflection is occur when there are external force applied on the board and then causing deflection and bending. So here it is example of the bending and deflection. So here is internal moment, positive internal moment, and here is negative internal moment. So we can relate the internal moment to the radius of curvature. We also call it rho of the elastic curve. So radius of curvature rho is appear after the deformation of the board. We can see here is before deformation and here is after deformation, and this is the rho, which is radius of curvature. So next, to derive the deflection equation, here we have first equation which is coming from relationship between the normal strain and the internal moment and the radius curvature of the board. So 1 over rho equal to negative epsilon over y. So according to Hooke's law, so epsilon, which is elongation, equal to sigma over elastic modulus, and also sigma also equal to negative m for bending moment over I for initial. Then substitute 1 over rho equal to m over ei. So here we will get, after we substitute these both equation, and then for the formula of curvature coming from the equation of elastic curve. So elastic curve 1 over rho equal to d squared v over dx squared. Then final equation we will get d squared v over dx squared, we get m over ei. And then from that equation just now, so we can differentiate each side respect to x to substitute and substitute v equal to dm over dx. Then we will get here the differentiate, and then ei d to v over dx squared equal to vx, and then we can differentiate again to get wx. So with those three equations just now, we can use to find the maximum deflection of the board. Then we can compare the maximum deflection with different material, which is we use is aluminium and wooden. Then next is strain energy. The strain energy is when forces are applied on the board, it will deform a material and provide the zero energy loss. And then because the work done by the force will be converted into internal work. It means the strain energy is coming from the internal work that causes by the normal or the shear stress. So to determine the strain energy, we can use the equation of elastic strain energy in a member when it's subjected to bending moment. Now, to the derivation of the strain energy equation, then the equation of strain energy is coming from the elastic strain energy, which is du equal to 1 over 2 sigma epsilon dv, and then substitute sigma equal to elastic modulus and epsilon. So strain energy we will get integration of sigma squared over 2e dv, and then substitute sigma equal to my over I, which is my is bending moment and I is moment of inertia. And then the final equation we will get strain energy equal to integration of 1 over 2e my over I squared dA dv. dA dv is substitute of dv, and we substitute dv, and then we get dA over dx. So after we get this final equation, we can use it to find the strain energy of the diving board, and then we can compare it with different material, which is we use is aluminium and wooden. That's all for me. Thank you.
Assalamualaikum and hello. My name is Zuliman bin Hamzah, and I'm going to explain about the calculation for the strain energy of the beam. The first calculation discusses about how to find the maximum deflection of the beam. This cantilever beam supports the triangular distributed loading as shown in the question. Any calculation involving engineering subject must start with a free body diagram. This step is important to list and find the internal load that will be used for the next calculation. The problem is how to find the internal load and what method that we can use to complete this calculation. If the elastic curve of the beam is difficult to establish, it is suggested that the moment diagram will be drawn first. Using the beam sign convention from the left side of the cross section, where the positive internal moment will be anti-clockwise and the shear force will be downwards. Therefore, if the moment diagram is shown, it is easy to construct the elastic curve as shown in the diagram. So, the moment function for the free body diagram with M acting in positive direction of anti-clockwise, the segment on the left is shown above. The equation for the distributed loading for the moment function is M equals to negative W naught x squared over 2L times x over 3 minus px. We have the moment of inertia. The moment of inertia is a constant where the value can be obtained from the basic formula of inertia moment for a square shape. It is I equal to 1 over 12 times bh to the power of 3. Next, we must find the elastic strain energy due to bending of the cantilever beam. by using the strain energy formula, which is UI equals to L integrate from 0 to L m squared over 2 EI dx. So by substitute the function moment of m, we can get the strain energy formula as shown in the slide. Then we must find the elastic strain energy due to bending of the cantilever beam for two materials, which is aluminum and wood, by using the strain energy formula that we obtained from the slide above. For aluminum, we use the elastic strain energy and substitute all the value that we obtain. For the elastic modulus or Young modulus, for the aluminum we have 69 gigapascal, and for the I, which is the moment of inertia, we obtain the value of 1.0125 times to the 10 power of negative 6, and then we calculate to get the strain energy for the aluminum of 107.37 joule. To find the strain energy of the wood, we must use the same formula for the strain energy that we find for the aluminum. So using the same formula, we substitute all the value. The value for the formula are all the same except the elastic modulus or the Young modulus of wood, which is 3 gigapascal. So by calculating, we find the elastic strain energy of the wood is 2469.78 joule. So as I can conclude that the calculation of one for the elastic strain energy, wood has more elastic strain energy than aluminum.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Alim bin Zakaria with metric number CD200-187. Now I will present about the calculation for this project. For the calculation, we separate into two parts, which is we want to find the deflection of the beam, and the another one is we want to find the strain energy of the beam. So my part is I will present about the deflection of the beam, while the another part is strain energy will be present by my friends Zuliman. So we go through the equation. So what the problem right now? So this problem is about the beam. So we want to find the maximum deflection of the beam, which is we use the cantilever beam. For this cantilever beam, as we know, we already have the moment function, but this beam is different because we use two different material, which is aluminium and wood material. So what is the difference for this material? We get the elastic modulus for aluminium is 69 GPa, while the elastic modulus for the wood is 3 GPa. So what is constant in our calculation right now? So the initial moment will be constant. The value of initial of moment, which is we call as I. The another problem is we have external load that happen to the this beam, which is we have the triangle distributed load. Okay, for the end of this calculation, we compare of this answer, which is we find the maximum deflection of the beam with the different two material, which is wood and aluminium. So we go through the step of the solution. Okay, the question right now, we want to find the maximum deflection of the beam. What beam is a cantilever beam? So we have the external load. This one of the external load 0.6 kilonewton, and this one is the distributed triangle load. We have 13 newton over meter. The length of the cantilever beam is 500 cm or 5 meter. And first step is we have to find the inertia of moment. So the inertia of moment, we use the formula is I is equal to BH power of 3 over to 12. So we get the information of the cross-section cross area is the 3 minus by 55 cm. So we put all the information into the formula of inertial moment. 0.45 meter and 0.003 meter. So we get the value of inertia of moment. So the value is 1.0125 minus by 10 power of negative 6 meter power of 4. So next step, we have to draw the free body diagram. Why must we have to draw this free body diagram? It is important to any analytical method or any analytical problem in engineering solution, because of we have to find the internal load. So right now we have two internal load that happen in the beam, which is first one is we call as moment, and the another one is we call as shear stress. Okay, so this one is for the elastic curve free body diagram, which is we see here, this is the maximum deflection that happened in the beam. So the maximum deflection happen where x is equal to 0. Okay, so right now we have the external load, which is we call as P, and this is the another one external load from the distributed triangle. Okay, so now we go through the another step. So we find the moment of function. This is important in this solution or this problem because of we want to get this moment of function and put into the formula of elastic or equation. After that we can see. So this moment of function, we do the cross section for the left side. So this is the cross section for the left side, and we get the internal load, which is M and V. But for this problem, we are not using the V because the V is not important of our solution, but the moment is very important. So that's why we have to find the moment of function. So now we can see here we use the compatibility method, which is we find the axial load of the distributed triangle load before, and we get the moment of function. So this is equation of moment of function. So next we have the elastic curve equation. So this elastic curve equation, we just use this one. Okay, I d power of 2 v over dx power of 2 is equal to moment. So this moment is we use from the moment of function before. We put all the moment of function into this equation, and we integrate into two times. For first time is this one, and we get the C1, and the another time we integrate, we get this equation. So for this equation, we get C1s and C2. This is we call as boundary condition. So this boundary condition, we have to find the equation of boundary condition. So the equation of boundary condition, how we want to find this equation is, we can see here the constant of integration are obtained by applying the boundary condition where v is equal to 0 and x equal to L, and the symmetry condition that dv over dx is equal to 0 and x equal to L. So how we want to put the value of V is equal to 0 into what equation? So first of all, we want to find the C1. C1 we can get from the V is equal to 0. We put the V is equal to 0, okay, into here. Okay, for the equation. So when we put the V is equal to 0, we put the X equal to L. So the X we change into the L, and then we get the particular solution. Okay, sorry, so for this equation, three equation, we can call as a general solution. For, okay, as we know, the general solution is solution, the equation where the boundary condition, when we put into the general solution, we can get the particular solution. After this, we can see the particular solution when we put the boundary condition. So when we substitute all this information into the equation of this and this, we get the C1 and C2. So for the C1 and C2, this is the initial condition, or we call the S boundary condition. So for the boundary condition, we put back into the equation of elastic curve before, and we get we can miss for all the C1 and C2 before, and we get the particular solution. So these all the particular solution. So when we have find the particular solution, what's next is, as we know before, as I present before, the maximum deflection happen when the x is equal to 0. Okay, so when x equal to 0, there will happen the maximum deflection. So we put all x equal to 0 to this both equation, and then we can get the equation of maximum deflection. So this is equation of maximum deflection. We have not finished yet, because we want to put all the information from the beam, which is we have two material before, right? So what is the material? So we have aluminium and the wood. Okay, this is final answer. So for the aluminium, we put all the information, just different is the elastic modulus value, and we get the Vmax for aluminium 0.380211 m/s, and for the wood is we get the 8.7449 m/s. So which one is the bigger maximum deflection? As we can see here, wood is bigger than aluminium. So that for my part for the calculation to find the maximum deflection, which we use different material, which is wood and aluminium. So that's all for me. That's all from me. Thank you so much.
Assalamualaikum. My name is Muhammad Irfan bin Saiful. So right now I'm going to talk about the simulation of our project diving board. So firstly, this is our aluminium diving board that have been drawn by using the SolidWorks, and then we also draw the wood diving board as a comparison for our project. And then this one is the study result for the aluminium alloy. So based on this drawing, we will know where is the main point of the force will focus, and then this is also the wood study result, where we also know where is the main force that is focused. So finally, what we can conclude from this simulation is that different material have different types of elastic modulus while having the same value of inertia. While for our project, we use the value of 3 GPa and 69 GPa for aluminium for the elastic modulus. So what we can finally conclude is that the velocity of wood is much higher than aluminium. Thus, this will cause the diver to jump higher because the board will deflect more, for the reason of the The value of wood is much smaller than aluminium. So that's all for me. Thank you.
For the conclusion, based on the calculation, the maximum deflection of the beam have different values with different materials. The board that made of wood has the highest strain energy than the aluminium because the value of Young modulus of wood is smaller than aluminium. The best material that suits for the diving board is wood because it has higher elastic strain energy which meets the requirement for the diving board.